Okay, so next up, we've done light cones, we've done the Minkowski metric. I want to look at collisions, or in this case, an explosion. Okay, so this is a space-time diagram for an explosion. Okay, we start off with this object here that is a has a red half and a white half. Okay, or a red call it a red part and a white part. Okay, and then it explodes. Okay, into part A, which is red, and part B, which is blue. Okay, and this is C here. This is the center of mass. Okay, so what we observe in this explosion is the whole thing was initially at rest. Okay, so initially the whole thing was at a velocity of 0. Okay, and we observe that the red half is moving at a velocity. Let me make this clear. This is speed of light times t. This is x. Okay, so the red part is moving at a velocity of negative 1/2 c. Okay, and when you have your y-axis is c times t, it's what that means is it goes one box horizontally for every 2 boxes it goes vertically. Okay, 1/2, 0.5. Okay. Similarly, the blue half is going in the positive x direction at a speed of 1/2 c. Okay, it goes 1 box horizontally for every 2 boxes it goes vertically. Okay, and this is what we observe. We observe that they're moving at the same speed. How do we know they're moving at the same speed? Well, you can draw a line like this and a line like this and observe. So this is at one moment in time, the distance in the center of mass reference frame, the distance to each object, and you can see, oh, they're the same distance away. Okay, that clearly means they're moving at the same speed in opposite directions. So how do the masses compare? It's probably obvious to you intuitively how the masses compare, but I just want to write it out. Okay, so MA times VA plus MB times VB equals the sum of MA and MB times the velocity of the center of mass. Okay, this is just how things work. This is how center of mass works. Okay, so now plugging in here, part A, okay, is moving at negative 1/2 c. Okay, part B is moving at 1/2 c, positive 1/2 c, and that equals MA plus MB. Sorry, MA plus. There's a plus sign in there. Trust me. Okay, times what's the speed of the center of mass? 0. Okay, so now what does this tell us? Well, first of all, the right-hand side is 0 because it's multiplied by 0. You can basically take out the 1/2 c's from both, and you can go negative MA plus MB equals 0. And what that gets you is that MA and MB have to be the same. Okay, and this is nothing special. This is exactly how it would work in classical mechanics. Okay, an object that's initially at rest explodes. The two halves going opposite directions, and at some time in the future, after the explosion, you notice that they are both the same distance from the center of mass. You could then conclude they have the same mass. Okay, nothing special here. Okay, we'll just circle that. Okay. Now, what I want to do, this is all in the center of mass reference frame. So this is the center of mass reference frame because the center of mass is here, C, it's at rest. Okay. I want to look at how this looks in red's reference frame. Okay. So over here on the right-hand side, we're going to do this in A's reference frame. Okay. So in A's reference frame, A is stationary. Okay. So let me draw, let's see, how do I want to do this? I'm going to do this like this. I have a line there, so we'll do something like that. Okay. And A goes like this. Okay. And here is A's space axis. Okay. So this is X for A. This is C times T for A. Okay. Okay, so this is now the reference frame of A. The center of mass is moving at half the speed of light, right? If A is moving away from the center of mass at half the speed of light, then the center of mass is moving away from A at half the speed of light. This is just symmetry, okay? There's a symmetry between A and C, okay? So the speed of C has to be half the speed of light. It has to be going the opposite direction as A is going relative to the center of mass, okay? You get the idea. So I'm going to draw this out here. And then notice I'm going 1 block horizontally for every 2 blocks and 1 vertically from the origin. Okay, so This is how the center mass is moving. Right there. No big deal. Now, here's the tricky part. Stupid. Sorry. Stupid phone ringing. Okay. So, the tricky part here is, hang on a sec. Yeah. Okay. How fast is B moving in A's reference frame? And you might think, well, B is moving at half the speed of light relative to C, so we just add them up, and we go half the speed of light, one times C. Doesn't work that way, okay? Here's how it works. Remember how we determined that they're moving, A and B are moving at the same speed in the center mass reference frame by saying this distance and this distance will be the same. Well, this distance here, these measurements were defined along the x-axis of C, okay? So what direction does that go? Well, the angle of the x-axis of C, okay, is the reciprocal of its velocity, okay? So this here is x for C. And what that means is we have to draw these things parallel to this line, okay? So let me see if I can dash that out a little bit to, okay, make it clear what that is, okay? So I'm going to go to here, and looks like we'll go here. Oh, not like that. Let's see. So this spot here, I've got to go now 2 up for every, or 1 up for every 2 I go horizontally. So I've got to go like that, and then also like this. And what I'll tell you now is this distance and this distance are the same. Okay, this goes 6 horizontally and 3 vertically, and then we go 6 horizontal and 3 vertical. Count them if you want. So B now has to pass through this point. Okay, so I'm going to draw B's world line. So here's the explosion, okay, and then B has to pass through that point. And not quite. Let me do it again. That's about right, okay? So now this is the world line for B in A's reference frame. And you can see clearly B is not going at twice the speed of C. And if you draw this and this, if you look in A's reference frame, the velocities don't have that same relationship, okay? So what the hell is the velocity of B relative to A? Well, so in A's reference frame, first let's write down the velocity of C, okay? So the velocity of C is plus 1/2 of the speed of light, C, okay? Velocity of the center mass here. Now what do we get here? Let's see, what I'm going to do is basically measure vertically. I'm going to measure to this point here, okay? So vertically we have 15 little squares, and then horizontally we have 5 little squares, 10 little squares, 11, 12, okay? So the velocity of B equals positive 12/15 of C, which is 4/5 C, okay? Now, what does this tell us about the masses of A and B over here, okay? So we have to use the same equation for the center mass. This is the center mass location velocity equation, okay? So center mass velocity equation. So we go MAVA plus MBVB equals MA plus MB times VC. Okay, well, let's see now. MA, we don't know MA, we don't know MB, okay? So VA in A's reference frame, we're doing this calculation now in A's reference frame. In A's reference frame, A has a velocity of 0, okay? In A's reference frame, B has a velocity of 4/5 C, okay? So plus MB times 4/5 C, and that equals now MA plus MB times 1/2 C, because that's the velocity of the center mass in this reference frame. Okay, so let's see now what we can do with this. So this term goes away, and I'm going to cancel out the C's. So what we get now is 4/5 MB equals 1/2 ma plus 1/2 mb. Okay. The common denominator between 5 and 2 is 10. So I'm going to go 8/10 mb on the left-hand side. And then on the right-hand side, we're going to have a 5/10 mb, so I'm going to subtract that over. So minus 5/10 mb equals 5/10 ma. Okay. So now, on the left-hand side, we get 3/10 mb equals 5/10 ma. And finally, we get mb equals 5/3 ma. Notice in the other reference frame, we got ma equals mb. What this means is that mass, or what we call inertial mass, okay, because there are different kinds of mass. There are different ways to talk about mass. So we got to be careful here. Inertial mass, oh, sorry, that's too many S's. Inertial mass depends on velocity. Or you can say inertial mass depends on your frame of reference. Okay, parentheses there. Okay, and it turns out that it follows a rule basically where, and I don't really have space to write this out, where m prime, so the inertial mass of something in motion, okay, equals gamma times its mass when it's at rest. Okay, and gamma is, remember that factor, gamma is 1 over square root 1 minus v squared over c squared. Okay, so things that are moving faster have more mass, have more inertial mass. And this sort of explains why it's not possible for something to go at the speed, for something with mass to travel at the speed of light. Okay, because as you approach the speed of light, this factor gamma approaches infinity. And so if you have an object moving at some high fraction of the speed of light, every little increase in velocity takes a greater and greater push. And so you get to the point where the force required to accelerate it would approach infinity. Okay, so there's no finite force that can bring something to the speed of light in a finite amount of time. Okay, I'm going to stop this one here. The next one will go on and talk a little more about mass and what the hell all this changing mass stuff is really about.